okay? And we could describe this with an equation. Go back. Same equation. I'm not going to do any problems like this. The mass times the heat of vaporization now will tell you how much heat does it take to turn so many grams into gas. Just like we did going from liquid to solid, or from solid to liquid, this is the same thing, except now this number will change. Instead of heat of fusion now, this is heat of vaporization. They're in your book, okay? Just multiply the two together, it'll tell you how much heat it takes to turn it into a vapor.
Is that saying the mass times the change?
This term is called the heat of vaporization. It's not change anymore.
It's not there.
Huh?
You changed the slide.
Wrong way.
So depending on the question, and that will tell you.
No, it's written out. So this is not.
Will it always say heat of vaporization?
Well, it'll talk about it's going from a liquid to a gas. That means you need the heat of vaporization.
Because it'll just have that triangle.
Yeah, this triangle here is because it is a change in heat.
Right, okay. We have to
Okay.
figure out what's changing.
And it's a fixed number. This is how much heat it takes to execute this change. Okay? But that's a good question, though. What does a triangle mean there? Because we said earlier, normally a triangle means change, right?
Mm-hmm.
And it does mean change. It means you're changing states. Okay? Same equation, just like heat of fusion. So we're not going to do another one like that. Now, there's another process. Before, I'm going to insert a slide. Let me go back. So we've talked about going from a solid to a liquid, and from a liquid to a gas, right? And these are both two-way streets, right? Well, scientists often think about it as a triangle like this. Because a lot of people think about, you get ice, you heat it up, it turns into liquid, you continue heating, and you can turn it to a gas, right? But you can also go from a gas to a solid, or a solid directly to a gas, without going through a liquid state. And you've all seen this before.
Yes.
Where?
How does gas go to a solid?
Well, I'm getting ready to tell you. Where have you seen it?
I saw it in my chemistry class.
In your chemistry class.
And also physical science.
Okay. Where have you seen it? Dry ice is a great example of this. Who's ever been to a concert or watched a concert on TV and they see the big smoke effect? That's dry ice. It's if I bring a chunk of dry ice in here, it's solid carbon dioxide, and I sit it on the floor, will it melt?
No.
It'll just turn into a gas. It'll go straight from a solid to a gas. Okay? And then you say, well, okay, I can buy that because I've seen that, but I've never seen anything go from a gas to a solid. Liar. You probably saw, well, what time did you get up this morning? It was still cold when you went outside this morning?
I got early, gotta do my work.
Not dude.
Not
Where you see it at?
The ice and frost.
Frost. Frost looks a lot different than if you get dew and then it freezes. If you get dew and then it freezes, you get little ice pellets, right?
Yeah.
But frost is these pretty little crystals, right? That's because it went directly from a gas to a solid. Where else do you see it go directly from a gas to a solid in nature? Does water ever do that in nature besides frost? What's the student's favorite weather event? Snow. Snow started as a gas and then changed directly into a solid. That's why it looks the way it does. Because if it turned into a liquid and then into a solid, what do you get then? You get sleep, right? We don't like sleep. Snow, yeah. Snow's pretty to look at for a day, then it's like, done. Right?
Y'all make the most of snow down here. I've never seen so many snowmen rolled up out of one yard. think it's
Okay.
every bit as
So,
slow.
have you seen this before? Okay. The process going from a solid to a gas is called sublimation. Sublime. It's sublime. Sublimation. The process going from a gas to a solid is called deposition.
Hold on. Wait, what is sublimation again?
Sublimation is solid to a gas. And deposition is gas to a solid. They're on the slide right there. See? Here. Right there. And just like freezing and melting, they happen with the same amount of energy, right? It takes the same amount of energy to make something sublime as it does to make it deposit. It's only heat in or heat out. Okay? Yeah. Okay, we already talked about heat vaporization. We're not gonna do this problem. We do want to talk about heating curves and cooling curves. As I said, it really is kind of a cycle, right? But most people don't think of it that way. And it's kind of hard to reproduce that sublimation deposition thing unless you have the right conditions. Most people think about if I had ice and I added heat, what would happen to it? Okay? Well, anybody here already work in a doctor's office or a vet's office or anything? They have super cold freezers, don't they? Some of them do. You know what the temperature is in that freezer? It's not just like zero, like the one at your, it's colder than the one at your house, isn't it? So if you took some ice out of that and you added heat, what would happen? Would the ice melt immediately? What has to happen to it? The ice has to get up to what? 0 degrees Celsius. So if you took that ice out of the minus 40 freezer, which is what a lot of them are, minus 40 Celsius, you warm it up, it has to get to 0 before it can melt. This is a warming curve or a heating curve. Here we start with our ice down here. It has to get up to 0 before it can melt. Once it's at 0, it melts, and then it's all liquid, and then the liquid heats up, and then we get to here, and what happens here? It all boils, and then up here it's a gas again. Note, let's look at these two flat parts right here. Erase this so we can see. Let's look right here and right here. What's happening right there? Temperature is staying the same, but what about the heat? There's more heat being added. Remember I said degrees Celsius or temperature is not the same as heat? I'm adding heat and the temperature's not changing. That tells me the two are not the same thing. Right? How long will it stay at that temperature? Well, it depends on how much mass you have. Till it's all turned into gas. Or down here till it's all melted. Okay? Fair enough? Okay. This is a heating curve. So the flat parts mean what? What's happening on a flat part?
Absorption.
It's absorbing heat, but it's constant temperature. Why is it constant temperature? Because something's occurring. What's happening on a flat part? Boiling or melting, which are what? Examples of? Change of state. Okay? The state is changing at these points. Okay? That's why the temperature doesn't change, but you continue to add heat. Okay? Fair enough? In between, or on the ends, all you're doing is heating up something. Nice straight line. you can look at it in the opposite direction. You can look at it as a cooling curve. Look, we start with steam, we cool the steam down to 100, it all condenses, then the water gets cooled, and it all freezes, and the ice gets cold. Now here's a question that somebody this morning in 152 asked me, because they're talking about some of this stuff too. And I told the story in my last class about how I've never seen anybody get burned by fire really bad, thank God, because I know it's a horrible thing. But the worst burn I've ever actually personally witnessed was a steam burn.
Oh, yeah.
Steam burns are bad. Why is it worse to get burned by steam at 100 degrees C than by water at 100 degrees C? You can use this graph to show that.
Matter of losing heat out of your body.
Yeah, watch. If you pour 100 degrees water on you and it's going to go down to 20 degrees C, this right here is how much heat you're going to have to lose out of your body to cool it down. But if I put the same amount of steam on you at 100 degrees C, this is how much heat you're going to have to lose. That make sense? So that extra heat is the heat of vaporization. The amount of heat that it takes, that it has to lose to turn from steam back into water. And it's got to give that heat to somebody. What happened was my dad set we had a wood stove in the house, and he set an empty kettle in the sink and reached across the top and turned the water on. Mm-hmm. The water hit that kettle and turned into steam and came up and hit his hand and his arm. It was bad. I heard some quality words that night. Woo! Yeah.
So is the heat that's being removed, is that from the item that condensation, the steam hits?
Yes,
Or
because
from-
the steam has more heat than your skin does. So what does it do? It transfers that heat into your skin. Heat always goes from things that have more heat to less heat. Steam has a lot of heat. So it's going to put it all into your skin, and it will continue to put it in there until the two reach the same temperature. So the steam has to condense, and then the hot water has to cool down to body temperature. And it keeps putting that heat in there until they get to the same temperature. Yeah, that's
So if
why.
his hand wasn't in the way of the kettle, the same thing would be happening when the steam hits the top of the kettle, but the kettle
Well, yeah.
is the one that gets cold.
When the steam gets someplace, well, the steam starts cooling down as soon as it leaves, right? And it transfers the heat to the air around it, right? And eventually it'll condense someplace, right? So if you had a window pane right above it, and the steam came up, it would transfer its heat to the glass and condense on the glass and cool down, right?
It happens in the hood of your oven all the time.
Happens in the hood of your oven all the time, that's right. Yeah. Like if you have a pot of water boiling, well, like mine, I have a built-in microwave above it. On the glass of the microwave, you see condensation all the time. Why? Because the steam out of the pot, right, condensed up there. It had to transfer its heat, become a liquid, and then that liquid cooled down to the same temperature as the microwave was, right? The glass on the microwave is cooled, right? So, but it has to get rid of that heat, right? When it hits your hand, it's going to give up the heat just like it does when it hits that glass until the two get to the same temperature. Yeah. All right, a couple questions. We're almost done. What does a plateau or horizontal curve part of the heating curve represent? It represents temperature change. Good, temperature staying the same, isn't it? Constant temperature? Yes. Change of state?
Oh.
Yes, that is what it is. It's change of state, right? The slope part on the heating curve is what? Is the temperature change? Yep. It's on a cooling curve, it's a decrease. On a heating curve, it's an increase, right? It's not a change of state. It's not constant temperature. It's an increase in temperature. Using the cooling curve, you should be able to answer these. You should know most of these anyway. Water condenses at a temperature of, what is condensing? It's the opposite of turning into a vapor, right? What temperature does water boil? 100 degrees C. Okay. At a temperature of 0 degrees C, liquid water does what? Does it freeze? Liquid water can freeze. Liquid water can't melt. It's already liquid. Right?
Right.
Okay. As long as we're good on that. At 40 degrees C, water is a liquid. How hot is 40 degrees C? Anybody know? What's body temperature? We did that the other day. It's actually in the lab. It's in the lab for the week. 8.6 Fahrenheit, what is that, Celsius? Would this water feel warm or cool to you? It's not that hot. Just a little bit over 100.
Oh, it's 39.
37 is normal body temperature. So it's warm water, okay? When water freezes, heat is added or removed? It has to be removed to make it freeze. And we are not going to do combined heat calculation. Sick baby problem. Remember the sick baby problem?
Oh, no,
You weren't there for the sick baby problem?
I might have.
We're not going to do sick baby problem. You can calculate how much ice you need to bring down a temperature a certain amount. We're not going to do that. We're not going to do that. We're not going to do that. Bless you.
Thank you.
And that's the end of chapter 3. All right, before we go, stop, listen.